All right, let's look at the theorem 3, perpendicular bisector theorem. All right, so let's say L is the perpendicular bisector. All right, perpendicular bisector is a line that go through the midpoint of the segment AB, and also it's perpendicular. All right, and we look at the set S, which is a collection of points which are equidistant from A and from B. So S is a point that the equidistant, same distance away from A and from B, right? And then conclusion is the perpendicular bisector is exactly the same thing as the collection of equidistant points from A and from B, right? So let's prove that. Alright, so in order to establish the equality between two sets, L and S, we're going to do mutual containment. So we're going to have to show that the L is a subset of S, and then we're going to have to show that the S is also a subset of L. Only way mutual containment can happen is that they are the same set. Alright, so let's do this containment first. Let's show that the L is a subset of S. Right, so let's do an element chasing. Right, first the L is a perpendicular bisector, so M is a midpoint. So of course AM and a BM are equal to each other, and perpendicular bisector go through the midpoint, and it has to be perpendicular. So those are just given. Right, so let's do the element chasing. So I'm gonna choose any point say P that is in L, right? So that's just going to be given. All right, then try to show that this P is actually belongs to L as well, right? All right, first case, there are a couple cases we probably have to talk about. First case, right? Right, if P happens to be equal to the midpoint, or P happens to be not the midpoint of segment AB. So this is just all possibilities, all cases. All right, so let's do a trivial case. What happens 6? Right, let's assume that the P happens to be is the same point as the midpoint M. So this is case 1. So this is kind of a trivial case. All right, if P is equal to M, so AP equals BP. So 7. AP equals BP by combining line number 1 and the line number 6. Right? So which means that the P is equidistant from A and from B. So therefore 8 P belongs to S. Right? So that's the definition. S is a collection of equidistant points from A and from B. So we got that, right? So this comes from just a 7 and the definition. All right. All right. So in this case, we could show that the P is in S. And what if? So let's do the second case. 9. All right. Assume that the P is not equal to M. All right. So this is the second case, case number 2. All right, so which means that the P is going to be somewhere around here. So I'll just draw a P here. All right, then we try to look at the triangle. So try to form a triangle like this. All right, then another triangle like that. And let's try to establish the congruence between those two guys. All right. So one thing we can say is, let's see. line number 10. Right? So since it's perpendicular, we know that the measure of the angle, maybe I'll just say angle AMP is congruent to angle BMP. Right? Since they're both right angles, so it comes from line number 3. Right? And also 11, right? We know that the PM, segment PM, is congruent to itself by reflexivity. So reflexivity, we have that. All right, then we can establish the congruence between this triangle right there and that triangle right there. Right? So we say 12. We know that triangle AMP is congruent to triangle BMP. Right? Because let's see, side angle side, because side angle side, right? So side, so AM equals BM, which is from line number 1. Angle, it's line number 10. And the side, PM equals, so it's line number 11, right? So we have that. And the number 13, so we have a two congruent triangle. We know that AP equals BP, right? This is by congruent, corresponding parts of congruent figures, right? So since AP equals BP, we know that the P belongs to, so number 14, P belongs to the set S, right? So either way, we know that the P is in S, P is in S. So the conclusion is, we know that L is a subset of S by line number 4. This comes from just the number 13, right? So and let's see, line number 8. And also line number 14, right? So this is the conclusion, right? So this is the proof for the statement that L is a subset of S, right? So we have to do the other containment, so we're going to have to show that the S is a subset of L, right? So let's do that. So I'm going to erase this so that we have a little bit more room. Alright, so let's do the other containment. We want to show that the S is a subset of the perpendicular bisector L. Alright, so AM goes BM. The M is a midpoint of AB, so it's given. And the perpendicular bisector go through M. So these are just the givens. Alright, and 3. Alright, so let's do element tracing here. So I'm going to choose any arbitrary point P in S. Alright, so this is another given. Alright, so pick that, and let's see, 4. Alright, so P is going to be, so we have AP equals BP, and that comes from the definition of the set S, right? Alright, so let's look at that. So 5, if there are a couple cases we probably want to, since if P happens to be M, we can't form a triangle. So we're going to have to change, look at two cases. P happens to be M, or P is not equal to M. Right? So this is all cases. Right? And 6. Right? If you assume the first kind of a trivial case, if P happens to be equal to M, so this is our case 1, then we know that M is on the line L, so P is in L, right? So we're combining line number 2 and the line number 6, right? Then we're done with this part, right? Because P is already in L. Alright, so let's look at the second case. Alright, so let's assume that P is not equal to M. Alright, then we can construct a triangle. So we're gonna put the P up here. Right? Then we're gonna draw a triangle like this. So we know that let's see, AP equals B, so this is congruent to that guy, right? We know that this is congruent to that because M is a midpoint, right? Then we can do this. So let's see, so we have let's see, 9. So line number 9, let's do it here. All right. So I'm gonna say angle PAM is congruent to angle PBM. Right? So this is since this is a PAB is isosceles triangle, because let's see, we're looking at since AP equals a BP, so line number 4 tells you that it's a isosceles triangle, and the base angles of the isosceles triangles are congruent. So this is using a isosceles triangle theorem, right, to do that. So we already know that this is congruent to that guy. Then we look at the triangle here. Alright, then we can say in line number 10, triangle AMP is congruent to triangle BMP by side angle side. So it's a side angle side. Right, side will be, let's see, we have, let's see, AM, BM equal to each other, so it's 1. So this is equal to that. All right, angle would be here, line number 9, basically angle there and an angle at B. All right, then S would be AP equals BP, so line number 4. Right, so this is 9. It's kind of hard to see. Maybe I should rewrite it. So this is line number 9. All right, line number 9. All right, so we have that. So we have a congruent triangle here and here. Right. So that means that here we just have to show that, let's see, 11. Right, we know that angle AMP is congruent to angle BMP, which is corresponding parts of congruent figures. And also, these are linear pair, so we know that measure of the angle AMP plus measure of the angle BMP is equal to 180. So this is a linear pair, so it's using A4. Right? Alright, but the combining 11 and the 12, we know that since they are the same measure and the sum is 180, so each one is 90. So we know that number 13, we know that the measure of the angle AMP is equal to measure of the angle BMP, which is equal to 90. Right? So we know that here PM is a perpendicular bisector. So we have 14. So since PM is a perpendicular bisector, maybe I should say L is equal to, right? L is actually equal to line PM. So of course P is going to be on that line, right? So this is what we want. So we know that here perpendicular bisector, so we know that this is 90, so it comes from its 13. Alright, so therefore 15, right, we know that therefore S is definitely a subset of L. So I'm using 3 and line number 7 and line number 14. Right? So combining both proofs there, we know that therefore, maybe I'll use red. So therefore, we know that the perpendicular bisector is exactly the same set as the set of equidistant point from A and from B. Right? So that's the perpendicular bisector theorem. Right? That's it. I hope that this was clear.